I'm just going to cover a few topics, and in fact I might even end early because I don't want to get into stochastic matrices until next class. And so I'm just going to focus on eigenvalue computations today. Start with computing the a to the n, which is the application of the repeated application of a matrix onto some initial vector. I'll talk about what it means, and then the similarity transformation and diagonalization, and then talk about principal eigenvalue, and then finding eigenvalues and some theorem, a good interesting theorem that goes with it. Okay, I guess the properties of eigenvalue. So I wanted to start with the physical meaning of a to the n, where a is this matrix. And so we've last time I ended with this notion of having the eigenvectors forming an eigenspace, and what happens is that if the vectors are even slightly apart, they're not aligned with each other, they're going to be a basis of a complex, in general a complex eigenspace. And so any vector can be expressed in terms of that basis vector is going to make it possible to compute a to the n. But we really didn't get into the physical meaning of a to the n. Yeah. Would you like to come up and explain what you're doing? No? Why not? You seem to be quite interested in explaining it to her. You're in the front row. You can see me? Yes? Then I can see you. Remember symmetric transformations? Yeah. If you can see me, I can see you. If you're talking to somebody, I can see that. Don't do it. If you want to talk, go outside. There's plenty of space outside, but not in my class. Okay, so the physical meaning of a to the n is quite important. And it shows up in control theory, which we'll get to in about a few weeks. But what you need to understand is that we can take an arbitrarily complicated path, and if we consider a small enough portion of it, it looks linear. So if you have something that goes like this, which is not linear, if you take a really small portion of it, it looks linear. Okay? If you took any small portion of it, it looks linear. And so what we can therefore do is to express this little step from here to here as a linear transformation. Okay? And that linear transformation could depend, let's say this is, just to put some values on this, let's just say it's a two-dimensional graph of x, and this is y, and so y equals some f of x. Okay, we can usually express y plus delta y as some f of x plus delta x. Okay, and so what we have over here is this delta x over here, and this little thing is delta y. Okay, this is just basic differential calculus. So what's going on is that we can basically write the y plus delta y as equal to fx plus f dash x delta x. Okay, this is just the Taylor expansion. Okay, and what we see is that we have this f dash, the first derivative, and it turns out that differential equations that involve first or second order and third order derivatives can all be expressed as linear functions. So what looks like a, you may think that a linear function has to look like ax plus by, okay, plus cz, but it could also look like this, ax plus bx dot plus cx double dot, right? Using the dot notation for derivatives. So what we're seeing over here is that this is also a linear function. So in the general sense of linearity, which we'll talk about in a bit, we will find that this is a linear transformation as well. Okay, which means that this trajectory, which is a two-dimensional trajectory, and when you take the Taylor expansion, is allowing us to express the way that y moves as a quote-unquote linear function. Okay, it's not linear in the sense of this linear, but it's linear in this sense, and we'll specify what that is more precisely. What I'm trying to get to is this intuition. Okay, and so what's going on is that I can take some arbitrary trajectory, and if I can write it in this form, then what happens is that this a to the n then represents, so this matrix A would then represent going from here to here in that trajectory. And then a square means going from here to here. And a cube is going from here to here, and so on and so forth. So the repeated application of A to the initial point really represents for us this, think of it as a simulation of the trajectory going step by step by step, where each step is an infinitesimal. Okay? And that's the whole power of having this repeated transformation. So we take some initial vector, we call initial state vector, x, and we can compute sort of x, let's call it x1. x2 is going to be basically a applied to x1. Okay? And then x3 equals a times a square, a square x1. I'm getting this confused here. A square x1. And in generally speaking, xk, the vector xk after k steps will be the a to the k x1. So what happens then is that we are able to sort of project outwards what's going to happen by applying a over and over and over again. Okay, so the ability to apply a over and over again is very, very important. Okay, to give you again a kind of intuitive understanding of this, let's say this is the share price of some share that you care about, Apple. Okay, and you want to predict what Apple is going to do, you know, let's say even 2 days from now. Okay, which is probably you can make a lot of money doing that. So if you can represent the share price of Apple as a differential equation in terms of its first derivative and second derivative, all right, then what you can do is you can basically claim that you can predict where the share price will be in terms of those derivatives by repeated application of the transformation matrix A, because A in this case, the transformation matrix, is just telling you what the trajectory is going to be. And so you can see right away that this becomes a kind of important matrix to get right, okay, because you're going to predict the share value and do all your trades based on that, okay. So I'm trying to just give you this motivation of why we want to do this, and this is because we can express these kinds of things, which include the first and second and general arbitrary derivatives, as what you would think of as linear functions. Okay, any questions about this? Okay, so that's why we care about a to the n. Okay, so now last time I talked about, you know, sort of the geometric interpretation of how to do a to the n. So let's just look at this. Let's say that we have some initial vector, let's start with this. Let's have matrix A, and let's say its eigenvalues, or eigenvectors, sorry. Let's say its eigenvectors are v1 and v2. Just to keep it simple, we just have two. Now remember, these are families of eigenvectors, so they all are, you know, there's a scalar associated with them. Okay, so it's an infinite family, but these are going to be all related to each other by scalar. So everything that falls in the V1 family is a scalar multiple of anybody else. Okay, so let's say there's some initial vector, I'm calling it so x, and x is going to be written as c1 v1 plus c2 v2, where v1 and v2 are the eigenvectors. Well, I used to do exactly the opposite notation in the text, but it doesn't matter, it's the same thing. So if you look at a to the n, so let's just look at a times x. Ax is the same as a times applied to c1 v1 plus c2 v2, where c1 and c2 are these constants chosen to make x. So x is a linear combination of the eigenvectors, which means that if the vectors span the space, we're going to find some combination of v1 and v2 such that we get x, and I'll show an example how that works. So then ax is this, which can be written as c1a v1 plus c2a v2, right? All I'm doing is expanding it out, and this is just simply expanding this thing out over here. C1, C2 are constants, and now we know that AV1 is the same as lambda 1 V1, where lambda 1 is associated eigenvalue. So we can write this as C1 lambda 1, V1 plus C2 lambda 2 V2. Okay, and so this matrix multiplication or the transformation has been replaced by a pure scaling operation with the value C1 lambda 1. And in general, it's easy to show using induction that a to the n x is going to be nothing more than C1 lambda 1 to the n x1 plus C2 lambda 2 to the n x2. Oh, sorry, V1 and V2. I keep getting these stuff here. Okay. All right, so what I'm doing is that the repeated application of A to the initial vector x is replaced by the linear combination of these two scalar exponents, okay? And that makes life much easier because remember we want to get to here, we want to compute the repeated application of A, but I don't want to do all the matrix multiplications. Instead, what I do is I just figure out the eigenvalues, the eigenvectors, and the corresponding eigenvalues, and then I can just do it kind of trivially, okay? And so I can predict the stock price, presumably. Of course, the hard part is to do this, right? That's sort of difficult. And okay, so all right, so let me do an example here. Actually, there's a homework example that let me just do the homework example first because it's an easy one. So we wanted to compute this one, 1941 to the 10 multiplied by 6 minus 4. So from the previous homework and last time's lecture, we know that the eigenvalues and eigenvectors corresponding to this are the following. So I'm going to just replace it. Let me see. I guess I'll do it here. So please exchange your solutions so we can do this. So the eigenvalues and corresponding eigenvectors are minus 5 and 1 minus 2 over 3. And then and 7, 1, 2 over 3. I'm going to actually leave this up because we're going to use it for the remaining homeworks. So we see right away that this vector is nothing more than 6 times 1 minus 2 over 3. Okay, so this is basically what I've been writing as V1, and this is the constant 6. So it's 6V1. So 1941 to the 10th multiplied by 6 minus 4 is just the same as 6 times minus 5 to the 10 multiplied by 1 minus 2 over 3. Okay? And that's it. That's the answer. So you can see I didn't need to do all this. So anybody who actually multiplied this out 10 times is should get a 0, okay? Because they just didn't get the point. Okay, so hopefully all of you got it, and and the whole point of this homework was for you to see how this fairly painful calculation of 10th power is actually trivial, and you don't need to compute 5 to the power 10. You can just leave it that way. Okay, but I could even do 100, and computation complexity is just very simple. Just where here 5 to the 100 is trivial, right? Because 100 times log 5 to the 5th or 6th decimal place. That's all you care about. E to the power hundreds or whatever. You can take 10 to the power 100 log 5. You can just do through logs. Whereas computation of this, you can't use logarithms. You're out of luck. Okay. So any questions about this? Yeah. Oh. No, that's right. Why did I choose what?
Choose 2 eigenvectors in general. Why not 3? Why not 1?
Why did I choose 2 eigenvectors? What do you mean by that?
Maybe we have 3 eigenvectors.
I see. The number of eigenvectors. First of all, there's infinite number of eigenvectors, right? Okay. How many eigenvalues do you have? If the matrix is a size 2 by 2. You can't have more than 2 eigenvalues because the fundamental theorem algebra says that the determinant a minus lambda I is going to be of power 2, right? If it's of power 2, there can be at most 2 roots, And those two roots correspond to two eigenvalues, and corresponding to each eigenvalue, there's an infinite family of eigenvectors. So since a 2 by 2 matrix, I don't have more than kind of 2 eigenvectors. But if I do 3 by 3, there would be more. Okay.
Right. We have one eigenvector.
If you have only one eigenvector, then the matrix is of size 1 by 1, which is essentially a scalar. So this is the simplest non-trivial example. Okay. If the matrix is of size 1, it's a scalar. So then finding the nth power is quite easy. So, you know, why bother? So we don't need matrix algebra for scalars. Okay. So, but, you know, all this power I'm illustrating with 2, but in general we'll be doing it for, you know, think of the matrix dimension as being 100,000 or a million, because in practice that's what you actually have, right? So 2 already 100th power is kind of complicated. Imagine a 100,000 by 100,000 matrix, which is routine, by the way. A 100,000 by 100,000 matrix is not something that people are, you know, even they don't even think about it. It's just pretty trivial to solve. Yeah. Okay. Any other questions? So in the latest issue of Communications of ACM, actually, I don't know how many have seen it. If you're not members of ACM, you should probably become members. Student membership is quite cheap, and the magazine, the Communications of ACM, is really worth reading. And the first article on the first page pretty much talks about a breakthrough at CMU about being able to compute for certain matrices the I guess the nth power, I guess the equivalent of that. But they can take a matrices of size 1 billion elements and do it on your desktop computer, you know, do matrix operations on those. So it's a real breakthrough. I didn't read enough of it to understand exactly what the breakthrough was, but this is still a hot topic for people to understand. Okay, any questions so far? Okay, good. So once we do this, I wanted to actually right. So then I want to give you couple of so the one trick that you need to remember is if A has distinct eigenvalues, okay. In other words, the equation A minus lambda I, okay, equals 0 has distinct roots. Which of course are the eigenvalues, right? If this is true, then life is really good. Okay, life is really good because what happens is that the corresponding eigenvectors for these eigenvalues are going to be forming a linearly independent set. Okay, so this is a very important fact. Okay, so you get in a large matrix, you do this, you figure out the roots. Now, by the way, how do you find out roots? It turns out there are some algorithms for finding roots. You can find the roots of any polynomial using these numerical algorithms. And I'll actually give you some names and so on when we talk about when we go into control theory. But in fact, if you just go on Google and search for root finding, you can go to these websites, you can just type in an arbitrary polynomial, it'll tell you the roots. Okay, so even for very large polynomials. So if you can get this polynomial, the characteristic polynomial of the matrix, you can find the roots, you can find if they're distinct. And if you can do that, and they're distinct, then the eigenvalues form a linearly independent set. So why is it important? Well, if the first, you have to remember again geometrically, remember, let's just take the two-dimensional case. Let's say this is the plane and I had these two vectors, v1 and v2 as being eigenvectors. These form a linearly independent set, okay? Which means that this vector cannot be derived from that vector. It's not a scalar multiple, okay? It's in a different direction. That's what it means. Which means any other vector, okay, any other vector in the plane, no matter where it is, can be expressed as a linear combination of the eigenvectors. Okay, and if you can do that, then computing a to the n is really simple because of this little trick you just saw. You just write the vector as a combination of the eigenvectors, and you can just basically compute it. It's really easy, right? So that's nice. But the other thing you can do, which is what I'm going to get into, okay, and then we'll stop after that, is this notion of the similarity transformation. And or it's also called diagonalization. And I'll tell you what we do as a recipe, and why it works is actually beyond the scope of what I want to cover. So I'm just going to give you the sort of the recipe for it. So basically, if we have distinct eigenvalues, then sufficient but not necessary condition, but it's sufficient okay, so distinct so sufficient condition so A has for A to be diagonalized, and this is not in most spell checkers mostly don't let this pass. Diagonalizable, okay, which means I can make it into a diagonal matrix. So specifically what we do is we compute the matrix X, which is like this. You have the eigenvector V1 here, the eigenvector V2 here, and so on until and eigenvector Vn. So the eigenvectors are written out as column vectors, and because these are linearly independent, we know that this is going to have a basis which is going to be full rank. So it has no redundant information in it, and then this matrix D, which is given by X inverse AX. Okay, that's X over there, is going to be a diagonal matrix. Okay, that's going to be a diagonal matrix. And why it is a diagonal matrix? Well, that's what I'm not going to tell you, but this is sort of a fact. Okay, so if you're distinct eigenvalues, you get a diagonal matrix. Okay, I'm going to take a break because I'm running a little bit over, and then after that I'll do an example to show what that is. Yes?
So has the eigenvalues on the diagonal?
On the main diagonal, correct. That's what the meaning of a diagonal matrix.
So if they have the eigenvectors,
right, then
they have the eigenvalues as well. So why do we calculate like this?
Okay, so the if we know the so let's put it like this. Let me repeat the question is, if you know the eigenvalues, why not just write down the eigenvalues? And the thing is, but to apply the matrix A onto initial vector, right? We need to know what these X and X inverse are, because D equals X inverse AX, right? But what's on the diagonal is not the eigenvalues of A. What's on the diagonal is something else. Okay, when you do the example, you'll see what I mean is that the diagonal elements of D are not the eigenvalues of A. Okay, the diagonal values of D are some things, okay, but it has some other contributions from X inverse and X as well. So yes, if you know the eigenvalues, I mean, you can't just write down D from that directly. You have to do some additional work. I'll show that when we do the example. Okay, so I'm going to continue with diagonalization, and I'll first do an example from here so that you could have the numbers here, and then I'll do the homework because there I didn't, wasn't okay. So what I said was that this particular matrix, the fact is that this matrix D is X inverse AX is diagonal. So let me give you an example from here. So let's say the matrix A is this matrix 4, 6, 12, 4. Again, it's sort of a simple. We can, in the book it goes through this, but we can find that the two eigenvalues are lambda equals 4 plus minus 6 under root 2, and you get this simply by taking the determinant, setting it to 0. It's a polynomial of degree 2, so it has two eigenvalues, and those are exactly 4 plus minus 6 under root 2, and the corresponding eigenvectors are 1 square root 2 and 1 minus square root 2. Okay, and as you can see, the two eigenvalues are distinct. 4 plus minus 6 root 2 are two distinct numbers, and so this gives us a matrix X as this one over here, 1 square root 2, 1 minus square root 2, like so. Okay, and that's just writing out this is exactly what I showed over here, as you can write out the vectors in column format. Okay, so then let's compute the diagonal vector D. So D is given by x inverse A x, and so x inverse, I'm just going to give you what it is. It's basically okay, 1 over minus 2 square root 2 minus square root 2 minus 1 minus square root 2 1. So okay, this value of x inverse is there is a formula in the book for how to compute the inverse of a 2 by 2 matrix that you can just kind of plug away. But in general, you can find the inverse by computing, computing the minors and so on and so forth. But let's just say this is what it is. So then A is given by this complicated expression, which is this x inverse. Okay, 1 over minus 2 square root 2. I'm just going to write it out. Minus 1 minus square root 2 1. That's x inverse. And then you have D, and A is just 4, 6, 12, 4, and then x, and x was 1, square root 2, 1 minus square root 2, okay? And you can simplify this using just matrix multiplication to find that the diagonal matrix D is given by 4 plus 6 square root 2, 0, 0, 4 minus 6 square root 2. In this case, this is just the eigenvalues of A. Now let me see. Why am I tying myself up? So in general, is that true? Is the diagonalization of A? Okay, I better go back and think about that for a minute. Yeah.
Even if we know all the eigenvalues, we can never know the order in which we have to put it on the diagonal matrix, probably?
No, I have a feeling that I'm missing something here, and I'm not able to think in my feet fast enough to tell you whether it's always going to be the case, because then Milad's question obviously is true. If I know the eigenvalues, why bother doing all this stuff? I can just
know the order in the matrix where we want to put the eigenvalues.
No, the order just depends on how I put it over here, right? And I can always put it in any arbitrary order over here. The order is not specified when I write it down like this. When I compute x, I'm sorry. Where is x? When I do x, I don't tell you the order. This order is going to determine what's going to happen over there. Okay. So, all right. So I'm just going to compute. Sorry, I'm going to go back and reread my textbooks and see whether it's always going to be the case. But nevertheless, it is true that this is a diagonal matrix. Okay. And in this case, it is definitely the eigenvalues. And so we can then compute basically a to the 5, which is what we want to do, we're going to compute the fifth power as basically nothing more than the eigenvectors, which is 1. Okay, so let me just do this over here. So a to the 5 is given by x inverse dx to the power 5, right? And which is going to turn out to be x inverse d to the 5x, okay? Because the way this works out is that, how do we do this? So let's just say to the power 2, x inverse dx to the power 2 is going to be what? X inverse dx, x inverse dx, okay? And then these two cancel out because it's just I, so we get x inverse d square x. And if you generalize that, there's going to be x inverse. So this to the power 5 is going to be this, x inverse d to the power 5x. Okay? And now I know what d is, I know what x inverse is, I know x, and so I can just basically plug it in here, and I get a to the 5 to be this horrible value, which is, I'm not even going to write it down, it's 157,783.99 something. There's some bunch of big numbers, you can look it up. But to do it, it was pretty straightforward. All I had to do was compute d to the 5. Okay, so I think now I can answer your question. In order to find a to the 5, I still need to know x inverse and x. So I mean, I can write down d without having to necessarily go through this computation. But to need a to the 5, I need x inverse and x. So, right? So it presumably, and I'll confirm this, you can just write down d by inspection. But certainly you need x inverse and x. So you need to do that work. And once you do that, then you can compute a to the 5. So you can't just know d to compute a to the 5. You need to know d, and you need to know x inverse and x. Okay? So, yeah, and so you do need to do that. Yes?
D equals x inverse ax should be a to the power 5.
Beg your pardon? Oh,
It should be d.
oh, sorry, yeah. What am I doing over here? Okay, oops. So we have wait a second. Okay, just give me a second over here.
It should be a to the power 5, then x inverse.
Right. Just a minute. What am I doing here? Give me a second here. Okay, so d equals x inverse ax, and right. So yeah, let's just do it this way. Okay. So you're right. D to the k, d to the m equals x inverse a to the m x. Okay. So now let me multiply both sides by x. So x d to the m equals a to the m x, right? And if I post multiply by x inverse, I get x d to the m x inverse equals a to the m. Okay, so I guess what you're saying is I need to flip it around. You're right. So so that a to the m is given by x d to the m x inverse. Sorry, it's not the way. Yeah. Okay, so who was it pointed at? So I think I made a mistake in writing it over here. So I need to write x d to the m x inverse, not the other way around. I flipped it around by mistake. But in any case, I still need the x and the x inverse matrices in order to compute a to the m. Okay. So any questions about this? Okay. All right. So what we have over here is finding a to the n and using the similarity transformation. So this is called the similarity transformation or the diagonalization of A to form D, because once you get D, you can plug this into here, and then you can find A to the m from D to the m, and life is good. Okay, so that's the first point I want to get across. So at this point, I want to just talk about a couple of properties of eigenvalues which are relevant and sort of interesting. So